Good morning, mis estudiantes. We're going to talk about the photoelectron spectroscopy method of analyzing atoms and the ionization energy needed to take away one of their electrons to make them a cation. Basically, what you're going to have to be able to do on the AP exam is recognize how the electron configurations are directly correlated to their photoelectron spectroscopy or PES graphs of any element. So I'll talk through some of the background and some of the theory behind this and the shell model, and then we'll do some examples, and then you're going to go online and do some of the examples that College Board has put out. So here we go. Okay, so the photoelectron spectroscopy is a new thing in our curriculum, and it really relates back to the quantum theory. All these electrons are in shells. Shells we all know are, let me get my pen going here. Shells we all know are related directly to the energy level. So anytime you hear the word shell or the shell model, you're thinking about the energy levels of the atom. And then when you hear the word subshell, we're talking about the sublevel, which we call S, P, D, or F, or G if you want to. So the photoelectron spectroscopy is trying to figure out how much energy does it really take to take away an electron from any of the subshells or from any of the shells within an atom. And that energy is directly related to the binding energy of an electron. The binding energy, as we go closer into the core of the atom, the inner core electrons, is going to be higher than the valence electrons. So a lot of this is a lot of text on this slide, and the next couple of slides is mainly for you to read. I'm not going to read it to you. But the inner core electrons have a higher BE or binding energy than the outer electrons, also known as valence electrons. They have a lower binding energy simply due to the law that you've got to be able to describe very well. I'm just going to put Q1, Q2 over D, which is Coulomb's law. The closer you are, the inner core, the higher the force of attraction. The outer shell, the farther away you are, greater the distance, the lower force of attraction. So we're going to relate this back to Coulomb's law as often as possible. Okay, so how do we actually understand the energy needed to remove an electron? We have to relate this back to the photoelectric effect, which is simply you are shining some sort of high energy wavelength onto a metal. A metal, a lot of times the electron configurations we're working with will be some metals, but you can carry this out throughout the periodic table. The photoelectric effect is where you take a high energy wavelength, which I'm going to usually use UV or X-rays, and it excites the electrons within the metal so much, and it's added so much extra energy, it causes the electron to eject. We like to say that it ejects because that's telling us that the energy was transferred and the electron became excited. So the process of photoionization can only occur if the photon has greater energy than the energy which is holding the electron in, which we call the binding energy. This is important because this is how we calculate the binding energy and the energy needed to remove an electron. This is from College Board. This is the big, humongous paragraph of information that you need to know about PES. This is straight from the curriculum, so I'll give you a second to read this, but notice that we're talking about how we relate the PES to the shell model, which we will talk about shells being the energy levels again. How the photoelectric effect is the kind of the evidence behind the PES, which is how much energy does it take to get the electron out of the atom. And then we're going to relate the number of electrons in a shell or subshell to the intensity of a peak on a graph. So the higher the peak versus a little peak means there are more electrons in that energy level. So I'm going to tell you how I go through and solve some of these too. So here's my first example. Oops. This is kind of what a PES graph looks like. Sometimes you'll just see one element in its individual PES spectra right here. So we all know that hydrogen only has one electron. That one electron is in 1s1. Therefore, this peak right here is representing the 1s1 electron configuration, or the 1s1 electron from hydrogen. Notice that this graph, and I've got 3 of them on here, but this graph has the energy in megajoules per mole, and so that's a lot of energy. The energy of the 1s electron of hydrogen is less than the energy requirement to take away the helium's electrons. Why? So helium is 1s2. So we're going to talk about this one now. Notice the different size in this peak and this peak. This one is in a ratio of 1 to 2, meaning that this only has 1 electron for the hydrogen, and this one has 2 electrons within the helium, because it's double the size peak. So you should see that intensity. I'll put intensity over here. You should see that intensity of the peak difference automatically. Then you'll notice that the electrons for helium are of higher energy. So this one's a higher number. Why? This is because hydrogen has a nuclear effective charge, or ZFF, of a +1. It only has 1 proton. This one, helium, has 2 plus because it has 2 protons. So relating that back to Coulombic attraction, helium has a tighter hold on its electrons than hydrogen does because of the charge of the nucleus. Coulomb's law. Okay, higher charged nucleus, higher hold on its electrons. Stronger hold means it's going to take more energy to remove these 2 electrons found in the 1s2 orbital. Lithium's our next example. How many electrons does it have? Let's write out the configuration. 1s2, 2s1. It has 3 electrons to work with. All right, so let's figure out where this lies. If we think about lithium, lithium also has 3 protons. That means that its nuclear effective charge is higher than any of the other ones we've talked about so far. So whenever you're writing out its electron configuration, you'll notice that this 1s2 is going to be the one that's closest to the nucleus. Looking here, you see that this triangle peak, it's supposed to be a peak, is twice as large as this triangle peak. So the twice as large nature of it means that this represents 2 electrons, while this one only represents 1 electron. Really what I'm doing in my head is I'm saying it's a 2 to 1 ratio. This 2 to 1 ratio means that this is double size peak than this one over here. So this has to represent the 1s2 electrons, and this has to represent the 2s1 electrons. So when we're looking at the energy differences, so looking down here at this axis down here, the 1s2 requires the most energy to remove those electrons than the 2s2. Does this make sense? Yes. The first energy level, especially the 1s, undergoes nuclear penetration, which means that it is strongly attracted to its nucleus, so it does not remove very well. You can't remove those inner core electrons very well, so it takes a high amount of energy, a huge amount of energy to get rid of those. The 2s2, 2s is the valence shell. Valence, if I can write this decently, is the valence shell electrons, so they're more easily removed, not greatly easily removed, but they're still the s block, so there's still a little bit of nuclear penetration, but this is a qualitative description right now. The 1s2 takes much more energy to remove than the 2s2. So the way that the AP exam is going to probably write these out for you is drawing it similarly to this one. And so what they said is they're going to pretend the nucleus is over here, and then as you're expanding outward, the shells are expanding outward to the right. So the first energy level, I'll use lithium as my example. Here's the nucleus over here, right here. The first energy level is here. There's our first shell. And then the second energy level is here. That's our second shell. So it's pretending like this is representing an atom, and then you'll realize that the closer it is to the nucleus, this positive charge over here, the higher the energy requirement to remove that electron. All right, so this looks like a big mess right now, but if you need to go back and write this down with me, that would be great. Okay, more information from College Board. Basically, the PES method of analyzing electron configurations all relates back to you understand what electron configurations are, how we got there, and Coulomb's law. So the electron, so I'll just read this basic bit to you. The electron configuration of the atom is described using electron configuration that reflects the concept of electrons in quantized energy levels or shells. Therefore, there's that shell model again. The energetics of the electron can be understood by consideration of Coulomb's law. So the greater the distance is high, then the attraction or force of attraction is low. So can remove those electrons much easier than if the distance is small. You can read through this. It talks about how we have shells or subshells, and the subshells I already told you are directly related to having S, P, D, and F levels within it for those orbitals. You can also read through part D here talking about the shielding of electrons, but you've gone through all of this already once you've gone through your periodic trends lecture. So if you need some extra help with some of the terminology, let me know, but I'm going to keep going through some examples for you. All right, so when I go through and I answer these types of questions, I always relate it back to electron configuration. That's if I know the atom. If I don't, I figure it out based on the graph. So it's all about the ionization energy, the energy needed to remove that electron. And usually we talk about removing the valence electrons, but this is why PES is so cool, because it can actually quantize the energy needed to remove any electron. Inner core is going to require more energy. Outer shell, like valence shells, can require less energy. It's all related back to the binding energy. Okay, so if you know the element, write the electron configuration first. And if you're trying to determine which peak represents which part of the electron configuration, look at the number of electrons, the ratio of the electrons from shell to shell or subshell to subshell. The number of peaks tells you how many sublevels there are. So if you have 2 peaks, then you only have 2 sublevels. My handwriting is great today. So that might mean you have 1s2 and 2s1 like we did for lithium. If you have, I'll go down to this example down here, if you have something like this, 1s2, 2s2, 2p6, you've got 3 peaks, 2 which will have the same intensity because we have 2 electrons and 2 electrons, so it's a 2 to 2 to 6 ratio. So the 2 peaks with the same intensity relate to the 2 that have the same number of electrons. The final peak is 3 times greater because it's the ratio of 2 to 6. So this is kind of a really helpful hint if you know how to read the graphs. Okay? So let's go ahead and try to draw some the relative differences between carbon, oxygen, and neon. And then we might quantize some of them, but I want to do the relative differences in their energies first. So yet again, we're going to pretend the nucleus is over here. Carbon has 6 electrons and 6 protons. Oxygen has 8 electrons and 8 protons. Neon has 10 electrons and 10 protons. Okay, and so like I said, I'd like to write the electron configuration first. So 1s2, 2s2, 2p, 2. Oxygen, 1s2, 2s2, 2p4. Neon, 1s2, 2s2, 2p6. Okay, so as we go through and represent these are actually, the peaks will actually be in order of the electron configurations because the 1s block is the closest to the nucleus and the 2p block is the farthest from the nucleus. So here's the carbon one. When we're thinking about the 1s between all of these atoms, who's going to have the hardest time being removed? Which electrons are going to be the hardest to remove? So that means you have to think about the charge of the nucleus for carbon versus oxygen versus neon. Carbon has a 6 plus, oxygen 8 plus, neon 10 plus. So neon's going to be the strongest attraction. So neon's little peak is going to be over closest to the nucleus. These are all comparatively, okay? Oxygen's going to be a little bit farther away, and carbon's is going to be a little bit farther away. So whenever you look at the energies on these, this will have a higher energy, and over here we'll have a lower energy. And this is energy needed to required to remove that electron. See how I put them all at the same peak level, the intensity level? That's because each of these contains 2 electrons, 2 electrons, and 2 electrons. So I want to write underneath it, I'm going to put 1s, 1s, and 1s. The differences are simply coming from the charge of the nucleus, the nuclear effective charge. I'll write that right down here, nuclear effective charge. All right, next we have 2s2 in all of these. 2s2, 2s2, 2s2. Same story. The 2s2 for neon is going to be of higher energy, requiring much more energy. So I'll put that peak here. And then versus oxygen, oops, not sure what happened there, and versus carbon, a little bit farther out too. So this is still 2s, 2 electrons, 2s, 2 electrons, 2s, 2 electrons. So notice again, same peak size, same peak size, same peak size, which represents a 2 to 2 ratio so far. So 2 to 2 ratio. For the carbon, our next one is 2p. 2p is going to be the farthest shell for or sublevel for carbon. So it's definitely going on the low energy side because it does not require as much energy to remove than the inner core ones. So here's 2p for carbon. 2p, 2 electrons, same size peak all the way through. So carbon has a 2 to 2 to 2 intensity ratio. So all of the peaks are the same size. Oxygen is a little different. We have 4 electrons in this P. And so I put the carbon's 2p orbital way out here. Oxygen's has to be a little bit closer in due to the fact that oxygen has a higher nuclear effective charge. So then this one's going to have double the peak size. This one has 4 electrons in it. It's still 2p4. But this should be about double in size. So the intensity ratio is a 2 to 2 to 4 ratio of intensity for oxygen. Lastly, we have neon, and neon has a stronger effective nuclear charge because of the 10 protons there, and it's going to have triple the electrons. So this peak's going to go way up here. It's a beautiful peak. 2p6 electrons. So this should be approximately 3 times the size. It's not great, but it's approximately 3 times the size. So the relative intensity is a 2 to 2 to 6 ratio here for intensity. So notice though that this one's also closer in because of the mere fact that it's a higher attraction on the inside and the inner core. So if you had to look simply at these ratios and the intensities of the peak and where the electrons are in relation to the closeness to the nucleus, which represents higher energy required to remove, you would have to identify a sequence of elements that could relate to these graphs. You could do that. All you would have to do is simply not look at, let me see if I can cover this up for you. Oh, that's a triangle. Not look at these. And then all you're doing is you're only able to look at, one thing here. All you can see is the fact that you have 2 peaks, 2 peaks, 2 peaks, which represent the same size peaks. So they're going to be starting from the lowest, 1s2 and 2s2. And then notice that we have a 1 to 2 to 3 ratio for the last one. So then your 2p something is going to be different as you go. So you could definitely do that. You just have to know how to read these. All right, take a minute and look at this practice question. You've got nitrogen and oxygen. The photoelectron spectra above show the energy required to remove a 1s electron. So this is not a full spectra, it's just the 1s. Go ahead and see if you can figure this one out. Oops. Looking. If you're reading, you'll notice that the nitrogen's peak is here, a little bit farther out, but this is of lower energy than the oxygen's peak. Oxygen has a slightly higher peak, a higher energy level peak. If you need to, you can write out the electron configurations for nitrogen and oxygen. How many electrons does nitrogen have? 1s2, 2s2, 2p3, and oxygen has 1s2, 2s2, 2p4. But we're all talking about the 1s2 electron or 1s electrons that are being removed. So then you have to think about it. Nitrogen has 7 protons, whereas oxygen has 8 protons. So knowing that, you should say, okay, oxygen has a higher effective nuclear charge. So when you look down at your answer choices, Nitrogen has half the p field? No. There are more electron-electron repulsions in oxygen than nitrogen? Maybe. Electrons in the p sublevel of oxygen provides more shielding the electrons in the p sublevel? No, not really. We're not even talking about the p at all. Nitrogen has smaller nuclear effective charge than oxygen. Yes, that's perfect. Okay, so here's a couple of links for you in terms of just some extra resources. You have a couple worksheets that you're going to go through and try to do, and some stuff from College Board. These are some really good relationships that I think that you need to know. So I would recommend watching either 11 or the 18-minute one. But I also think that after you do the worksheets, you'll feel much more comfortable with this. This link here for the chemarizona.edu one is going to be a resource that's on another worksheet, which I'm going to show you. Okay, let me come back to this one. This is the first worksheet. This is in your packet. It's about 6 pages long. It's got Model 1 through Model 2 through Model 3 on it. And they use EV, which is the same thing as megajoules per mole, so do not get confused. I think you should do that one first because it's going to hold your hand as you go through some of this, and it's going to refer back to Coulomb's law quite a bit. This second worksheet has a link on it, and this is a webinar offered by College Board. I already watched it, and I've taken notes on it, so you'll see like this is the first page of many pages. The questions that you're mainly going to be responsible for are sample questions 1 through sample questions 1 through 6. So the answers are told to you on the link itself, but I took these notes as I went through and I copied and pasted some of the models and some of the descriptions. So if you want to print this out, you can. But I also typed up some extra notes, but you're only really responsible for doing the questions. Really good questions because College Board put them out, so that's what I would expect to see on your exam. The last thing is the extra resource that's going to be having the chemarizona.edu link on it. This walks you through how to do a couple more PES, and it talks to you about the relative differences between a lot of different atoms. This is a resource I found online. It's also posted on the website, so I recommend this one as well. The last question we're going to do is the magnesium one, just in case you ever see one with the tiered effect of all of the PES put on top of one another. Oops, this is simply for magnesium, and you'll notice that we have 4 peaks. So if you write out your electron configuration for magnesium, 1s2, 2s2, 2p6, 3s2, 4 peaks come from 4 sublevels. So that should make sense. So when you're going through and trying to label them, this one is of 126 electron volts or megajoules per mole. This one's about 9. This one's about 5. This one's less than 1. The peaks are hard to tell the intensity, so they go ahead and give the ratios to you: 2 to 6 to 2 to 2. Well, duh, that makes sense. 2 to 2 to 6 to 2. So which one is of the highest energy? The highest energy one is going to be the one that's the inner core electrons. So the highest energy, this 126, is going to be the 1s2 electrons. The next highest energy, the 9, is going to be the 2s2 electrons. The next highest energy is going to be the 2p6 electrons. And then the final, the valence electrons, will be the 3s2. So this right here is the valence shell, where this right here is the most inner core shell. So when you're looking at these questions, this one's telling you, if they told you magnesium, which peak in the spectrum represents electrons that are closer to the nucleus? The ones at 126 electron volts. What's the relevance of the relative height of the peaks at about 5 and about 9? The ones at 5.31 say there are 3 times as many electrons than the one at the 9.07. You'll see that you have I'll just do 6 to 2 ratio since it's a 3 to 1 difference. Last one, why is there such a large difference in energy between the peaks of all the peaks here? And the simple way to explain it would be Coulomb's law. And you can explain that a little bit further by saying the charge of the nucleus and the charge of the electrons over the distance they span will increase the force with decreased distance, or vice versa, decrease the force with increased distance. The increased force reflects a higher energy on the PES. The lower force of attraction reflects a lower energy on the PES. So if you're comfortable with recognizing the magnesium and then going from there, what about if you didn't know it? Assuming the PS data all shows the electrons present in the atom, identify the element. You would have to say 4 peaks, and 4 peaks represents 4 levels. And you know the levels. You know Aufbau's principle. You know that it starts off at 1. 1s something, 2s something, 2p something. Well, these have to be filled. This has to be filled. The last one is going to be 3s. I don't know. But if you look at the peak differences, you can identify this based on their intensities. Still applying the assumption A, which specific electrons are associated with the 126. This is where we get back into the highest attraction. Highest attraction equals the inner core. The inner core is the 1s2 electrons. What does a relatively low value of energy tell you about the relative position of the electrons in any atom? That means that it's far, far away. Far away means they're the valence shell. They're the outer shell of electrons. Okay, so hopefully you are a little bit more familiar with this. You can try this last bit one here, but I'd like for you to practice the other ones on the other worksheets. Have fun. Let me know if you have any questions, and I will see you soon. Oops.